Hello everyone, thank you for signing into my live stream. I'm Mr. Matt and this is Dr. Todd. And thank you very much for watching. Welcome to Algebra I. Today we're going to talk about the absolute value and piecewise functions. These are a little bit strange to some students. Piecewise functions are conglomerations or combinations of many different functions that really don't have to have any relationship to each other, but they're restricted over different intervals of domain. So domain is a fancy word for the acceptable values of x that you can use for a particular function. So what you're going to see is that piecewise, and a special type of piecewise function is a step function that literally looks like horizontal steps that are climbing. We'll talk about that in a later session. But piecewise functions just look like cut and splices, cut and pastings of different functions together over different intervals of the x-axis. So let me go ahead and share my screen with you. There we go. So, and just remember that this is a live stream, so the connection between the iPad is a little bit delayed. There's a little bit of delay over the internet, so I'll try and keep that as flush as I can with the broadcast screen. The overarching theme here is that piecewise and step functions are combinations of segments of two or more functions. The determining factor of which function occurs at a particular point is the domain of the overall piecewise function. The domain tells you what function you should use within a certain interval of x values. So, first of all, domain is just a fancy word for the acceptable values of x. In other words, it describes what input values you're allowed to use. And what we're going to see is that the result of this is you're going to have a whole bunch of different functions, like I said before, just like cut out just particular sections of a function, kind of pasted next to another particular section of a different function. We also need to talk about inclusive versus exclusive domain. So when we see brackets around a certain value, that means that the domain is inclusive. That means that it includes the endpoints. If you see parentheses, that's usually indicative of an exclusive domain. And that means that it does not include the endpoints. Now, graphically speaking, a solid dot on a graph does the same thing as brackets. That means that it's an inclusive to that point. So instead of the overall domain being inclusive, just that specific endpoint is inclusive. So if it ends on 3, that means we can count 3. Conversely, a hollow circle means exclusive. So really it just depends whether we're using a list format, we'd use brackets or parentheses. And if we're using a graphical format, if we're looking at the graph of a certain piecewise function, we'd use hollow or solid points to indicate whether that value is included or excluded from our consideration. And what you'll see is this allows us to overlap the function. So we might have like two different lines. Let me do it like this way. So we might have like two different functions like this, and they both share this one point here, but this one might have a solid dot and this line might have a hollow dot. So this function doesn't accept that input value right here. It's this function that counts. So if we're talking about like straight lines. So let's look at some examples here. So we want to graph the following piecewise function. So I'm going to give you 3 minutes just to think about this. And the notation here means at this specific interval. So when x, for example, you'd start by just drawing a Cartesian plot, which is just an x and a y axis. Right? So this guy's x and this guy's y. And you could just mark off some points. Now it says when x is less than -2. So I'll start off just by drawing some guidelines here. So x is equal to -2. You're going to have to decide what function occurs to the left of that. And then they're talking about in the second function, when f of x is equal to 3, that occurs between -2 and +1. So +1 is right here. Well, that's not, you can do better than that. Let's see. That's a little better. So you need to decide which function occurs between those two bounds of -2 and +1. And then if x is greater than 1, f of x is equal to 4. And also remember, when you have a function that's just set equal to a number, that's a horizontal line. So that's a little bit of a hint. But I want to give you 3 minutes just to think about this problem. I'll keep track of the time right here, and I'll update it every minute. And then I'll give you the solution. Okay, so looking at this function, it says f of x is equal to 2 if x is less than negative 2. F of x is equal to 3 if negative 2 is less than or equal to x, which is less than or equal to positive 1. That basically means that x, whenever x is in between negative 2 and positive 1. And f of x is equal to 4 if x is greater than 1. So first, notice how only the second equation had a domain that was inclusive to its lower and upper bounds. Everything else, the first one and the last equation, or the third equation, they have domains that are exclusive. So we have to take that into consideration when we're drawing the dots on the graph. And I completed the graph there. So notice that less than negative 2, we have a hollow dot, and then we have a line with an arrow facing negative, away from 0 to the left, going left from 0. The middle section is inclusive, so that's right here. And that's why the middle section has the solid dots. That stems directly from these signs right here. The less than or equal to sign and the other less than or equal to sign. If it's just less than or if it's just greater than, it's not going to be solid, it's going to be hollow. And the third guy, if x is greater than 1, y is equal to 4. So that's this horizontal line, but going in the opposite direction with a hollow dot because it's exclusive to positive 1. It can't be positive 1, but it must be greater than positive 1. If you have any questions, then please let me know. Otherwise, I'm going to give you 3 minutes. Please look at this function, and I want you to graph this function. After a minute and a half, I'll start to graph it as well. Okay, so I drew an x and y axis here, and then I drew in the bounds of the domain that we're talking about from as given right here. So you can see that we're talking about whenever x is less than or equal to +2, whenever +2 is less than x, and x is less than +4, or in other words, in between +2 and +4. And lastly, whenever x is greater than or equal to +4. So I just drew in those bounds there. So when x is less than +4, we're talking about the function x squared. And what you can do is just draw a little table here. So if we're talking about y is equal to x squared, and we just want to get a few values. So let's say when x is equal to -4, when it's equal to -2, 0, and then we need to know what it's equal to at +2. So if I put -2 into x squared, I'm going to get 16. Excuse me. If I put -4 into x squared, I get +16. If I put -2 into x squared, I get +4, because -2 squared is +4. If I put 0 into x squared, 0 squared is 0. And if I put +2 in, 2 squared is +4. So at -2, I am at +4. So this value is on my plot. At 0, I'm at 0. And at +2, I'm at +4. Now, at +2, I'm inclusive to the domain. So this is going to be a solid dot here. And then I'm just going to connect the other dots. This is a parabola. And so it's going to continue somewhat like this. Looks like a U. Or it should look like a U. But notice the function stops on the right-hand side because it's restricted by its domain. Now, in between 2 and 4, we're bound by the function 2x. So let me do that in another color. And let me get some room here. So if y is equal to, if y is equal to 2x, and we make a table here, and we're concerned about the x values of +2, +3, and +4, at least those are the integers that lie between the bounds, or those are the integers that lie within the domain of this function for this particular equation. If I substitute 2 in for x, then I get 2 times 2, which is 4. If I substitute 3 in for x, then I get 2 times 3, which is 6. If I substitute 4 into x, or 4x, I get 2 times 4, which is 8. So at 2, I'm going to be at 4, but that's going to be a hollow circle. At 3, I'm going to be at 6. I'm just going to put a little guiding dot there. And at 4, I'm going to be at 8. And again, at 8, I am exclusive to that value. So this is going to be a hollow dot here. So the purple segment has 2 hollow dots. It's just that it's overlain with the solid blue dot. But the purple function should have 2 hollow dots. And then g of x, I'll do that in this color right here. G of x is equal to 8 when x is greater than or equal to 4. So 8 is just a horizontal line. We don't need to do any tables for that. That's just going to continue, straight to the right, and we're going to draw an arrow to represent that it continues infinitely. And this is going to be solid because it's inclusive. So the purple function would be hollow, but the gold function would be solid, and the blue function would be solid at its bounds. If you have any questions, then just let me know, but that's what that graph should look like. Let's do one more. I'm going to give you 3 minutes. Please look at these segments of this piecewise function and graph the overall function. Okay, so I started drawing out some tables there. So if we look at the first segment where x has to be less than or equal to positive 2, we're guided by the function negative 3x plus 9. And I did that over in this like kind of cranberry color. So y is equal to negative 3x plus 9. So in the domain, we're leading up to positive 2. So I'm interested in the input values of positive 2 and just a little bit less than positive 2 so I can get a general idea of what the line, how it's sloped, how it's shaped, or in what direction it's going and how steep it is. So I'm going to test the values 0, 1, and 2. When I plug in 0 for x, I just get positive 9 because 0 times negative 3 is 0, 0 plus 9 is 9. When I plug in positive 1, I get positive 6 because negative 3 times 1 is negative 3. Negative 3 plus 9 is positive 6. When I plug in positive 2, I get positive 3 because negative 2 times positive, negative 3 times positive 2 is a negative 6. Negative 6 plus 9 is going to give you a positive 3. So graphing this, we're going to be inclusive because it's less than or equal to positive 2. So we're inclusive to positive 2. That's going to be a solid dot. At x is equal to 2, y is equal to 3. So we're going to be at a solid dot. Whoops. Let me do this in the original color here. So we're going to have a solid dot at positive 3, and then I'm just going to map out some guiding dots. 1 is 6, and 0 is 9, so we have a function that looks like this. Okay, so solid dot and then an arrow facing towards negative infinity on the x-axis. In between 2 and 3, we're guided by 2x plus 2. I did that in orange, so when x is equal to 2, y would be equal to 6. So I'm going to have a hollow dot at, oops, I'm sorry, that's at 3. So we're going to have a hollow dot at 6, and we'll have a solid dot at 3 when x is equal to 3, y is equal to 8. So 8 is right here. And then let me do, when x is greater than 3, we're guided by y is equal to 3x minus 1. So if we draw out a little table here, we're starting at x is equal to 3. So let me just look at when x is equal to 3, 4, and 5. Plugging in 3 for x, we get 3 times 3, which is 9, minus 1, which is 8. If we plug in 4 for x, 3 times 4 is 12, minus 1 is 11. Plugging in 5 for x, 3 times 5 is 15, minus 1 is 14. So at positive 3, at x is equal to positive 3, we're going to be exclusive to positive 8. So we're going to have a hollow dot at positive x equals 8. Excuse me, at x equals 3, we're going to have a hollow dot at y is equal to 8. At x is equal to 4, the function is going to obtain a value of 11. So we're going to be about right here. And then at 5, we're at 14, so we'll be about up here. So we have a function that's looking like this. Just a sketch, so it doesn't have to be exact, but just so you understand which dots are hollow, which dots are solid, and how to generally graph the functions overall. If you have any questions, then just let me know. Otherwise, we're going to reverse this, and we'll do a few of these, and that will lead us up to the end of our session today, and in the following sessions, we'll have some more practice and get to the absolute value function, which is a special type of piecewise function. But for now, I'd like you to use the same concepts, but in reverse, to write equations for a piecewise function that corresponds to the following graphs. I'll give you 3 minutes, and then I'll give you the answer. Okay, so let's look at this guy. So first of all, it's helpful to look at which point the domain is divided, or at which points the domain is divided. So at x is equal to -2, we have a break. As x is equal to +2, we have a break, and when x is equal to +10, we also have a disjointed break in the functions. So we can start by just listing y is equal to, and then we have this large bracket because we're going to have more than one function. The left-hand side, when x is less than +2, we can write the domain if x is less than +2, and then we're going to write the function here, the equation. This is just a horizontal line, so this is just y is equal to 12. So y is equal to 12 if x is less than 2. Now the second domain is going to be inclusive to positive 2, but exclusive to +10. So +2 is going to be less than or equal to x, but x must be less than +10. And to calculate this value, notice that we have points 2, 2, and we have points 10, 16. So we could calculate the slope between these two lines. Remember that slope, or your m value, is equal to y2 minus y1 over x2 minus x1. So that would be 16 minus 2 divided by 10 minus 2. That's going to be 14 divided by 8, which is 7/4, or we will reduce down to 7/4. And you can take that and plug it into your mx plus b form. So y would be equal to mx plus b, and is the slope-intercept form. We know what m is now. M is 7/4. 7/4 x plus b. And you could take any one of these points, like 2, 2, and plug it in for x and y to solve for b here. So if we know that point 2, 2, we could have also used point 10, 16, but I'm just using smaller numbers because they're easier to work with. So if we know that 2, 2 occurs on this line, because we can see that it does, then we can plug in 2 for y, and we can plug in 2 for x. 7/4 times 2, and we can solve for b here. So remember, 2 can be written as a fraction as just 2 over 1, if that makes it easier to understand what's going on. 7 times 2 is 14, so this is 2 is equal to 14 over 2 plus b. So we're going to have 2 minus 14 over 2. It's a little bit of a review of fractions. I didn't mean this to be this long. But we can get common denominators here. We have 2 over 1 minus 14 over 2. So you can multiply this guy by 2 over 2 to get common denominators. And you'd have 4 over 2 minus 14 over 2 is equal to b. So that's going to be b is equal to -10 over 2. So b is equal to -5. So the long and short of that is that your function here, if b is equal to 5 and m is equal to 7/4, then y is equal to 7/4 x minus 5. And that is your function in between +2 and +7. So that was a difficult one, but that would be 7/4 x minus 5 if x is less than or equal to x and less than 10. The last section, I'll scroll down in a second and make sure that you have that work down. But just the last section is inclusive to the domain at x is equal to 10, and it's just a horizontal line at 6. So this guy would just be +6 if x is greater than or equal to +10. So I'm going to scroll down here and just make sure, give you a few seconds to make sure that you have that work. That was a complicated one. I didn't necessarily intend it to have all of those fractions in there, so I apologize. But I think that that is a useful review. If you have any questions, or if you have um, any questions at all on any of these steps, then just let me know and I'll do my best to explain it. Otherwise, I'll give you 3 minutes. Let's look at the same type of exercise, but with this graph. So I'll give you 3 minutes, and I'll start solving it as well at 1.5 minutes. Okay, so let's go through this. I started to solve just for time's sake. But this first portion, if we divide them by the domains, the breaks in the domains, we see that there's something going on at x is equal to 0. There's also something else going on at x is equal to 6. That's where everything is divided by. On the right-hand side, notice that we go from negative 8, 8 to 0, 0. So because they're the same value, it's like negative 8, 8, the change, and it's going to 0, 0. The change here is going to be the same. It's going to be 8 minus 8 minus 0 over 0 minus, 0 minus 8 over 8 minus 0, which is going to end up being negative 8 divided by 8, which is a negative 1 slope. So this is the graph of the negative x function, or y is equal to negative x. And that's if the domain is between negative 8 and 0 inclusive. So we have negative 8 less than or equal to x, which is less than or equal to 0. Then in between 0 and positive 6, we have a horizontal line at y is equal to 8. So we have y is equal to 8 if 0 is less than x, which is less than positive 6. And lastly, we needed to calculate the equation of the last segment. So I just took the two points 4, 12 and 12, 16, and I calculated the slope between them. So 16 minus 12 is 4, 12 minus 4 is 8, 4 over 8 is 1/2. So this graph has a slope of 1/2. Once I know that, I can plug it into the general form of y equals mx plus b, now that I know that m is equal to 1/2. So y must be equal to 1/2 x plus b, and then I can use any point on that line. I'm just going to use the smaller values, or the point that has smaller coordinates, of 4, 12. And so I get 12 is equal to 1/2 times 4 plus b. 1/2 times 4, and I'm sorry, let me move that up. 1/2 times 4 is 2, so we get 12 is equal to 2 plus b, and so b is equal to 10. So the actual equation here would be y is equal to 1/2 x plus 10 if x is less than x, which is less than or equal to positive 12. So that will take us up to the end of class today. If you have any questions, then please let me know. We'll continue on Friday with the absolute value function, and I'll also be posting recordings for the session that we missed on Monday, so that will be stream 1. I know it's going to be posted after stream 2, so I apologize for that illogical situation. But I want to continue on schedule, and I want to just go back and make sure that I provide those unique examples for you to have as a resource. But otherwise, thank you again for watching. If you find my videos helpful, then please like my streams and subscribe to my channel. But otherwise, Dr. Tot, do you want to say goodbye to everybody? Or are you sleeping? Dr. Tot, you want a cookie? You want to say goodbye? Come on, it's your job. You got to say goodbye to everybody. That's why we pay you the big bucks. Come on. You say bye, Paw? Paw? Okay, good boy. Thank you guys very much for watching. I hope you have a wonderful night, and I'll talk to you all on Wednesday. Excuse me, Friday.